Today we will have our 7th lecture on the basics of nuclear chemistry, and today we will talk about the nuclear reactions. We remember that there are different mechanisms of interactions of ionizing radiation with matter. It can be elastic or inelastic interactions, and inelastic interactions can be divided onto excitation and ionization. But there is another type of inelastic interactions. It is nuclear reactions. So let's see how long we know the nuclear reactions. Actually, the first nuclear reactions was already conducted by Rutherford in 1911, so it is more than 100 years ago. For this, he used just alpha particles that were emitted from the radioactive source of natural radionuclide, radium-226 or polonium-210. And due to these nuclear reactions, by irradiating the nitrogen, the normal nitrogen, with alpha particles, he obtained the oxygen and hydrogen. And to write these reactions in a shorter way, we can use these brackets, where you can see that on the left part, inside these brackets, we write the particles, the kind of particles that irradiate our target, that is also located on the left. And on the right side, after the comma, we write the particles that are emitted. In this case, it's just a proton. And after the brackets, we write the nucleus that is produced due to the nuclear reactions. Later, in 1934, Frederick and Irene Joliot-Curie discovered the artificial radioactivity by irradiating the aluminium foil also with alpha particles that are emitted just by natural radionuclide. And they observed the formation of the radionuclide. So they took stable element, aluminium, they irradiated it with alpha particles, and they obtained another radioactive material. So it was a first observation of the artificial radioactivity, and Frederick and Irene Joliot-Curie won the Nobel Prize for this discovery. Again, you can see this short notation of the nuclear reactions with brackets, where we write on the left the particles that irradiate our target, in this case aluminium, and the particles that are emitted from our target with the formation of this resulting nucleus or recoil nucleus of phosphorus-13. Yeah, in these schemes we can see how we can write the different types of radioactive decay if we use this type of diagram, this nuclide chart or nuclide map. If there is a number of neutrons on our axis, on our horizontal axis, and the number of protons on our vertical axis, then if we have any kind of radioactive decay, we can draw it with just an arrows going to the certain direction. For example, in the case of beta plus decay, we remember that there is a loss of one proton and increase of one neutron. Thus, we lose one proton, we go to down to 1 point, but increase of neutrons by 1, so the beta plus will be directed in this way, as well as the electron capture, and in all other radioactive decay types, we have this certain direction of our reactions. You can do these exercises by yourself to understand how we are moving with different types of decay. And the same is for the nuclear reactions. If we have like some starting nuclide and we irradiate it with some sort of particles, then we summarize the number of protons and neutrons from these particles, and then we subtract the number of protons and neutrons that are emitted due to the nuclear reactions. For example, let's take these simple reactions where we irradiate our target with neutrons, and as a resulting particle is the proton. So as far as we add one neutron by irradiating the target with neutron, we are moving to the right with one cell. But as far as one proton is emitted, that means that we should go down by one cell. So the whole direction will be in this way. Let's take, for example, gamma N reactions. So it is some photonuclear reactions induced by the photons with high energy. So gamma, there is no neutrons or protons. In general, we should stay in the same cell. But due to the nuclear reactions, there is emission of neutron, so there is loss of one neutron. And that's why we should go to the left by one cell. So we are moving to this direction. Again, you can do these exercises with any kind of the nuclear reactions that you can imagine, or with this kind of reactions that are mentioned here. It will be quite useful. Why the nuclear reactions are happening? Not due to the radioactive decay, but the induced nuclear reactions are happening. There is some simplified model that was proposed already by Bohr around more than 100 years ago. It can explain what is happening and what we observe when we are using different kind of particles that irradiate our target. So let's assume that we have some sort of nuclei, sort A of nuclei, and we irradiate it with some particles, some small particles. If the energy of the particle and the velocity of the particle is sufficient to form the compound, this combined nucleus, then it will happen. So our initial nucleus will combine together with this small particle, and they will form another nucleus that is called a compound nucleus or combined nucleus. And then what is happening further is dependent only on the composition of this nucleus, on the number of neutrons and protons, and the energy state of this combined nucleus. In some cases, nothing is happening. The initial particle and the initial nucleus, they are going just in different directions, and in this case we are talking about the just elastic scattering. Nothing is happening. In another case, our nucleus, so they also disintegrated to the initial particles, but our nucleus are now in the excited state. And in this case, we can say that part of the energy of the particle is converted to the energy of our nucleus, and in this case we are talking about inelastic scattering. So part of the energy is going to the big nucleus. But in some cases, the energy state and the composition of nucleus is so that this combined nucleus disintegrates to another particles that are different from the initial nucleus and initial particle. And in this case, we have either nuclear reactions where the small particles is emitted from the combined nucleus, or we can have different kinds of nuclear reactions with another types of nucleus, or it can be even a fission of the combined nucleus when the nucleus splits onto two more or less equivalent parts. This is happening when we are talking about the heavy nucleus like uranium and plutonium. Then we undergo the fission reactions, and we observe this formation of not only one heavy nucleus, but two heavy nucleus and some small particles as well. As far as all the nuclear reactions are going through this combined nucleus, and all the products of the nuclear reactions depending on the composition and the energy state of this combined nucleus. That means that it's not really important what are the initial nuclei that we have and initial particles that irradiate our target, let's say. Because if we take different nuclides, in this case it is gallium and zinc, and we irradiate it with different particles, but these particles together with the initial nucleus gives us the same number of protons and the same number of neutrons. Thus, from different initial compositions, initial nuclides, we can form the same combined nucleus, the same intermediate nucleus. And then all the products will depend only on the composition of this nucleus. You can see in this example that so it is experimental results on the formation of different products when we irradiate gallium target or zinc target with protons in the case of gallium, or with alpha particles in the case of zinc. And you can see that the distribution of the resulting product are more or less the same, independent on the initial composition of the nucleus, but there is a dependence only on excitation energy, or let's say the excitation energy of this intermediate nucleus. Again, if we know what we would like to obtain, we can choose the initial particles that irradiate our target, or we can choose the target that we can use dependent on the aim of our irradiation. Either we would like to obtain the nuclides that we can easily separate from another metal. For example, if we take zinc, in this case any of the nuclide that are forming will be easily separated from zinc. If we take gallium, in some cases we will form as well gallium, and in this case it will be impossible to separate the gallium from the gallium. So you see in this slide this notation sigma, this letter sigma, and some strange units like millibarn. So what it is? It is nuclear cross sections, and in principle, cross section, it is the probability that our nuclear reaction will happen. To estimate quantitatively the result of our nuclear reactions, we can calculate the number of interactions That will, of course, depend on the cross-section. Again, it is just a probability that these nuclear interactions will happen. And the higher the probability, the more interactions will happen. Then it is the number of nuclei in our target per unit area. And of course, the more the number of nuclei, the higher the probability and number of interactions. And this small n, it is the number of particles that are passing through this area, through this unit area. And again, the more the number of these particles, the higher will be the number of interactions. And the probability of our interaction or cross-section has a units bar, and it is the same unit as a unit area. So it is squared centimeters or squared meters, and it is 10 to minus 24 squared centimeters and 10 to minus 28 squared meters. And it is roughly correspond to the cross-section of one nucleus. So from these numbers you can estimate that the radius of one nucleus is roughly 10 to minus 12 squared centimeters. We can represent this cross-section as an area of the interacting particles. So if we have our nucleus that interacts with the passing particles, the cross-section will be somehow depends on the will be sum of the diameters of these two particles divided by 4. And we know that any particle, especially small particles like elementary particles, can be also assumed as a wave, and we can estimate the wavelength of these particles represented by these particles by this simple equation. And for any energy, we can calculate this wave number. You can see that the wavelength is inversely dependent on the energy. And that means that the higher the energy, the smaller the wavelength of our particle. And that means that if we have the fast neutrons or fast particles, then the wavelength or this diameter of the particles will be smaller if we compare it with the slow particles. In this case, the lower the energy, the larger will be the wavelength represented by our particle. That's why when we will see different cross sections for different reactions, we will see that the cross sections for slow neutrons will be usually higher than for the fast neutrons. It can be also explained by the time that the particles and during this time the particle can interact with the nucleus. You can imagine if the particle is going very fast, the time of interaction is very short. And that means that the probability that these fast particles will be captured by this nucleus will be also low. And that's why for the particles with the high velocity, the cross-section will be lower than for particles with the low velocity, small velocity. And usually the typical range for the cross-section is something from 0.1 to 10,000 barons. But in some cases, these cross-sections can be very large. And for example, for xenon, you can see that this cross-section is very large. It's 3 million barons. And this is the reason why xenon is a poisonous element for nuclear reactors, because it captures very effectively the neutrons, and there is no neutrons for uranium, and thus all the fission reactions are slowing down. But we will see it during our next lectures. So now you just need to understand that for very often for fast particles the cross sections are lower than for slow particles, but it is true for mainly for neutrons. In some cases, we can observe not just a decrease of cross-section with the energy of neutrons, but in some cases we can see these sharp lines at some certain energies, certain energy values of neutrons. And these lines, they correspond to the energy level of the excited nucleus. And so it is very convenient for the nucleus to catch the neutron and to be on one of the energetic level. We remember that every time when we have some field energetic level, it is favorable for the system to be at this state, at this energetic state. It can be nucleus at some excited state, or it can be just an atom with some excited electron orbitals. So in any case, when we have some field energetic level or some energy that correspond to this energetic level, we can observe this resonant or the very high absorption of the light, of the X-rays or whatever. And in this case, we can observe this resonant line for the absorption of neutrons, because these energies of neutrons correspond to the energy levels of the nucleus. We can just simply draw these levels as this, and at the levels that are close to the ground state, we can see that these levels, they are separated. That means that the difference between these levels is quite high related to the energy, and that's why when the energy of the neutrons is very small, we can observe these resonant lines. And the higher the energy, the smaller the difference between these levels. In this case, we didn't observe anymore the resonant line, but it now like a sum of all these discrete lines, and it becomes not discrete levels, but some a continuous region. Like in this case, we can see that the first level, then the second, and you can see that the difference between different energetic level becomes smaller and smaller, and finally there is just a continuous cross-section for nuclear reactions. Oops. This is also the case for the nuclear fission reactions that are induced by neutrons. Again, we can see that the cross section is decreasing with increase of the neutron energy. Again, because the cross section is inversely dependent on the velocity of our particle, and so the faster the neutron, the smaller, the shorter the time for the interactions, and that's why the cross section is decreasing. And but in some cases you can observe this resonant line as well. Okay. But sometimes, if there is some reactions that requires additional energy for the reaction, in these cases, the cross section of reactions will increase with the increase of the energy of the irradiated particles. And thus, we have to understand the energetic effects of nuclear reactions. In general, we can write this value of the energy that is released due to the nuclear reaction with this simple equation. It is the same as we wrote for the just the radioactive decay. So it is the mass of initial particles, so it is our mass of our particle of our nucleus that is irradiated, and the mass of particles that are irradiate our sample, and minus the sum of the masses of our recoil nucleus and the particle released due to the nuclear reactions, and then multiplied by this coefficient that is equal just to one atomic mass unit. So it is energy equivalent of one atomic mass unit expressed in kilo electron volts in this case. Of course, if we, due to the nuclear reactions, the heat can be released or can be consumed or absorbed, the energy. In the case if the energy is released, it is some energetic reactions like normal radioactive decay, or very often it is the neutron-induced nuclear reactions. But very often we can observe that the energy is consumed or absorbed. So that means that if we would like that these nuclear reactions will happen, we have to bring some energy to our system. And of course, if the energy is released, so it is spontaneous process, and there is no threshold for the energy of our particles. But again, if it is under energetic reactions, that means that we have to bring some energy. And how we can do it? Of course, this excess of the energy should bring the particles that irradiate our target. And the threshold energy that our particles must have, can be expressed with this equation. So you can see it's the quantity of the energy released or absorbed due to the nuclear reactions, and that this ratio between the sum of the masses of our product to our initial nucleus, or it can be expressed as this, where this member in the equation, it is the kinetic energy of this combined nucleus. It can be calculated very easily, and this threshold energy can be calculated very easily for the neutrons. So we can take just neutrons with this threshold energy. But for the charged particles, it is not so simple. because when they charge particles, it is positively charged particles like protons, neutrons, alpha particles, some other nucleus. When we try to combine the positively charged particle with the positively charged nucleus, then we have electrostatic repulsion, and the particles that should come to the nucleus, this particle should overcome the so-called Coulomb barrier or Coulomb electrostatic barrier, and we can calculate the value of this barrier knowing the charge of our nucleus, a charge of our particles, so it's just the charge of one electron. And if we know the radii of both of these particles, and then it can be expressed as this simple equation. And you can see that, and it is quite logical, that the higher the charge of our nucleus and the higher the charge of our particles that irradiates our target, the larger the repulsion between these two particles, and the larger the barrier, the Coulomb barrier between these two particles. And in this example, there is dependence on the Coulomb barrier for particles with different charges, for protons and for alpha particles. Also, when we increase the energy of, in this case, protons, of course, we increase the cross section of the reaction, because in this, the higher the energy of protons, the higher the probability to overcome the Coulomb barrier. But you can see that there is some decrease in the cross section of a certain reaction, but it is mainly because another secondary reaction, its cross section is increasing. Thus, as far as there is a limited number of probabilities, that means that if we increase the probability of another reaction, the probability of our first reaction will decrease. And this is step by step, this dependence of different reactions, their cross sections on the energy of protons. Of course, we can calculate some total cross section of the nuclear reactions, and but it is not so important for us, because when we use nuclear reactions, we normally use them for production of a certain radionuclide, and thus we are not interested in some total cross sections, but we are interested in some specific cross section for a certain reaction to obtain some certain selected radionuclide. Sometimes even if the energy of our particle is lower than the energy of Coulombic barrier, but higher than the threshold energy, so this energy of our particle is enough for production of nuclear reaction. And sometimes these particles, so normally they cannot overcome the Coulombic barrier. So you can see that Coulombic barrier in this case is very large. But as far as our particles are living in the quantum world, they can go into the nucleus due to the so-called tunnel effect. So they can somehow seep through this barrier and go directly to the nucleus. In this case, the cross section of such reactions will be very small. It will be something like 10 to minus 3 barns. But still, there is some possibility for particles to create these conditions for nuclear reactions. In this case, the cross-section will be determined by the transparency of the barrier, and normally these values are very small. So, we can calculate the energy for Coulomb barrier, thus we can calculate the threshold energy that our particle must have that the nuclear reactions will be possible. So we can combine these numbers, and we can say what is the exact energy that our particle should have, charged particle or neutron should have to overcome the Coulomb barrier, to that our reaction can happen. And again, it is about the energies of our initial particles. But what about the energies of the particles that are released due to the nuclear reactions? And we can take some simple examples of different types of nuclear reactions. We will start with some easy examples of N-gamma reactions. So it is reactions induced by neutrons, and the only particles that are released, it is the gamma quantum and the recoil nucleus. So you can imagine that in this case we will have the same element, so there is no change in number of protons. We just add one neutron to our nucleus, and thus it will be the same element but another isotope of our element. And as far as this combined nucleus, this intermediate nucleus will be in the excited state, then it goes to the ground state, it will emit some gamma quantum, gamma quantum photon. And we can calculate the energy of our gamma quantum that is released due to this reaction as this equation. So if we know the energy of our nuclear reaction that is released, then it is easy to calculate the energy of gamma quantum. It is when we took the energy of fast neutrons, this energy of fast neutron. In principle, the whole energy that is released due to the nuclear reactions and all the energy that our neutron brings to the system, all this energy will be released as a gamma quantum. So will be transferred to the gamma quantum. In the case of thermal neutrons, it is very slow neutrons with the energy very close to zero. And in this case, the energy of gamma quantum, again, even from this equation, we can assume that the energy of neutrons is close to zero. And in this case, the energy of gamma quantum will be simply equal to the energy of the nuclear reactions. Then photonuclear reactions, or in this case it is photoneutron reactions. In this case, the energy of gamma quantum that we will need to bring to our system usually is quite high, something like 10 to 20 mega electron volts. And the energy of the particles, in this case we produce neutron, and the energy of neutron can be calculated with this, again, quite simple equation. We should take into account the ratio between the mass of our initial nucleus and the mass of the daughter radionuclide. And if we have some reactions induced by neutrons, but we produce not the gamma quantum, but some particle, it can be proton or alpha particle, thus we can calculate the amount of energy that is transferred to the particle. And thus we can calculate again the energy of these particles for in the case of fast neutrons, or in the case of thermal neutrons. And there is an example of such calculations. Let's look deeply on this. So we have chlorine, isotope of chlorine 35. We irradiate it with neutrons. We produce protons and sulfur 35. And we know that the energy of this nuclear reaction is equal to 0.6, let's say, mega electron volts. And of course, the whole energy of the nuclear reactions will be distributed between the proton and the sulfur 35 due to the law of conservation of momentum and with the equation for kinetic energy of the particles, we can recalculate that the energy of sulfur will be equal to the energy of proton divided by the ratio of their masses. And the proton energy can be calculated as the energy of our nuclear reaction and the ratio of the masses of our particle and the resulted nucleus. So here it will be a mass of our resulted nucleus and the sum of the masses of the resulted nucleus and the resulted particles. In this case it is proton, thus the mass is 1. And we can calculate the energy of the released protons. And the same we can recalculate the energy of the recoil nucleus quite easily. What are the sources of neutrons? So we now know what the energy we should have for neutron for certain nuclear reactions, but how we can produce the neutrons. And there are three kinds of the sources of neutrons. First of all, here it's maybe not first, but I would say that first of all it is nuclear reactors, where we have a huge fluxes of neutrons due to the nuclear fission reactions. And the average energy of the fast neutrons that are released is equal to 2 mega electron volts. But as far as in most of the reactors we have moderators of the neutrons, so it is the material that decelerate our neutrons. We have a wide variety of energies of our neutrons, and a large part of them will have very low energies, so they will be thermal neutrons. Another sources of neutrons, it is so-called generators of neutrons. In this case, we use accelerated particles to induce nuclear reactions where the resulting particles released are the neutrons. Or we can use compact sources of neutrons. In this case, we use also nuclear reactions that are induced by the charged particles. But in this case, we simply use alpha particles that induce nuclear reactions with beryllium, for example. And as a result, we produce neutrons. So we put any of the alpha emitting radionuclides close to the beryllium, and we obtain the neutron source. There is a list of different neutron sources that are used in different applications. You can see that normally there is, as I told you, some source of alpha particle and beryllium that resulted in nuclear reactions producing the neutron flux. Depending on the availability of the alpha emitters, depending on the tasks, depending on the physical safety requirements, we can use any kind of these neutron sources. Interesting that there is a radionuclide californium-252 that emits neutrons as one of the way of its nuclear decay, so radioactive decay. We don't need to irradiate it with any other neutrons or any other particles. It emits neutrons as its normal process, its normal radioactive decay. Generated of neutrons. Again, in this case, we use the accelerated particles. We induce some nuclear reactions depending on the target in our system. In this graph, you can observe different types of targets that are irradiated by neutrons or protons. And depending on the energy of the irradiating particles, we obtain the neutrons with different energies, again depending on our task. What are the main results of the nuclear reactions induced by the neutrons? The most popular, let's say, it is the N-gamma reactions, where the initial nucleus simply captures the neutron with release of only gamma quantum and with the production of another isotope of our element. In this case, it is typical for thermal neutrons, and it is the main way how we capture neutrons and how we protect the human beings, the personnel, from the neutron flux. First we decelerate or moderate our neutrons with water, with other light atoms, and then we also have some specific elements like cadmium, for example. You saw that for this reaction, cadmium has very high cross sections, very large cross sections, up to 10 to 4 barn to 10 to 4 barns. And this is the way how we catch our neutrons. But this captures of thermal neutron is typical for almost any of the elements. So again, it is quite important and popular reaction. Another reaction is N2N, when we produce more neutrons when we add. And again, it is in this case, it is normally for the neutrons with high energy. As a resulting nucleus, we normally produce beta plus emitters, because there is a deficit of the neutrons. So we put on one neutron and we have a release of 2 neutrons. That means that in our resultant nucleus there is less neutrons than it was in the beginning. Thus we have an excess of protons, and the type of the decay, how protons are decaying, it is the beta plus decay. In the case of neutron-proton and NP reactions, in this case we normally produce the beta minus emitting radionuclides, because again in this case we lose 1 proton and we bring 1 neutron, thus we have an excess of neutrons. And we remember that in this case, when we have an excess of neutrons, we have a beta minus decay, because neutron decay disintegrates to proton and electron and antineutrino, and in this case again we produce beta minus emitters, as well as in the case of N alpha reactions. Here we have even larger loss of protons and a larger excess of neutrons. In the case of nuclear fission reaction, we produce a wide variety of different radionuclides. First of all, it is beta minus, because we just have much more beta minus emitters. Also, because these fission reactions are typical for the heavy nuclides. In such heavy nuclides, we have a greater excess of neutrons comparing to the lighter elements, and thus when these atoms or nucleus are splitted, that means that in these 2 parts we have an excess of neutrons, because initially it was a lot of neutrons in our uranium or plutonium, and thus as far as we have an excess of neutrons, we have predominantly beta minus emitting radionuclides. The main sources of charged particles, it is different types of cyclotrons that are used in research institutes, in medical facilities for production of radiopharmaceutical nuclides, radionuclides, and of course some accelerators. One of the most known accelerator is collider in CERN, so it is huge hadron collider, but it's some extreme accelerator. But in many research institutes you can find the accelerators of charged particles. It can be just electrons, or it can be protons, alpha particles, or even heavy nuclei up to uranium nuclei, depending on the construction of the accelerator. And also accelerators, of course, are used for production of super heavy elements. It is one of the example of the what is inside the cyclotron, and we will look deeply on the construction of this equipment in the course of the radiopharmaceuticals, when we will look on how different radionuclides for radiopharmaceuticals are produced. And for us, as the final topic in this lecture, is the amount of the accumulated radionuclide. And depending on the source of the particles that are irradiating our target, we will have different expressions, but normally the view of these expressions are more or less the same. So, what is it? The activity of the accumulated radionuclide will depend, of course, on the flux of the irradiating particles. The larger the number of the irradiating particles, the higher will be the number of the produced radionuclide and the higher its activity. Of course, it will also depend on the cross section of the reaction, on the surface area of our target, and on the time of the irradiation. And this expression is valid normally if we have a thin target, so we can neglect the absorption of the neutron flux or the charge particle flux inside our target, and we can neglect also the burnout of our accumulated radionuclide. If we have a thin target, so we can, it is the case when this ratio of the number of irradiated atoms divided by the cross section of the direction is smaller than 0.1, then we can rewrite this equation as in this case, where this N0 is the total number of the activated nuclei, or simply the total number of initial atoms that have these nuclear reactions that we are observing. Again, it is the flux of our neutrons. As far as we are talking about the reactor, it is the flux of our neutrons, it is the cross-section of the reaction, number of the activated nuclei, and again the time of the irradiation. You can imagine, so it is a very similar equation to the equation in the case of secular equilibrium. In the case of secular equilibrium, the multiplicator between the brackets was the activity of the parental radionuclide. In this case, normally when we activate the stable nuclide, we can say that the half-life is much larger, so than the half-life of our accumulated radionuclide, and thus so let's assume that activity of our parental radionuclide is constant and is equal to this multiplicator. Also, if you remember from the case of secular equilibrium, these brackets will be equal to 1, and then the time of the, in this case, irradiation is equal to 6-7 half-lives of our radionuclide. That means that after 6 half-lives of our accumulated radionuclides, we will reach a constant value of the activity of this radionuclide. In this case, it will be called saturated activity, and this maximum activity, this saturated activity, will be simply equal to this multiplicator. So it is phi, sigma, and N0. If we irradiate our target for a very long time, in this case, our accumulated radionuclide can also be burned, and in this case, the rate of accumulation of our radionuclide will depend also on the cross-section of these nuclear reactions with our radionuclide. Taking into account these possible nuclear reactions, we can calculate the activity of the radionuclide with this expression, with this equation, where this capital lambda is equal, or effective decay constant is equal to the decay constant of our radionuclide plus this parameter, so the probability of the nuclear reaction. And it is the representation of the accumulation of radionuclide that is produced due to the neutron-induced reaction. So again, this accumulation is according to this equation, and we can see that at some certain point we are reaching this maximum activity or this saturated activity. In the case of the radionuclides that are accumulated due to the nuclear reactions induced by charged particles, or we can use another expression, but very close to our previous expression. In this case, when we use accelerator, we control the number of the irradiating particles by the current of the beam of our particles. So the current, it is by definition the number of the charge that passes through the through some unit area per second. And thus, if we know the current of our beam, that means that we know the number of particles that are going through the unit area per unit time. And in this case, the activity of our radionuclide can be expressed in as this expression. But normally, for the thick targets, normally we use this yield, the thick target yield, that is noted just with letter Y. And these Y values you can normally find in some databases, in some reference books. And in this case, the activity of our accumulated radionuclide is expressed by this equation, where you can certainly find the same multiplicator as in the case of the as in the case of the neutron induced reaction, as in the case of secular equilibrium. So this multiplicator is always with us. And at the end of our lecture, it is important to remember that in all the cases when we use a neutron source, or when we use charged particles to induce our nuclear reactions, when we stop irradiation, when we take our target out from the equipment, from the facility, then we stop the accumulation of our radionuclide. And as far as it is a radionuclide, it is a radioactive material, it starts to decay. It always decays, of course, even during accumulation. That's why we have these brackets as a result of the solving the differential equations. So there is always a dynamic process of accumulation and disintegration of radionuclide, but finally it's the accumulation wins. But when we stop the irradiation, when we stop the accumulation of our radionuclides, there is only the decay of our radionuclides. And that's why it is important to know the half-life, not only to calculate the time that is required to obtain the radionuclide of certain activity, but also it is important to work in such period of time that we still have enough activity of our radionuclide and we can use it. It can be for some research purposes, it can be for medical applications, it can be also when we are calculating the time when our reactor is not working due to the poisoning by different radionuclides. So this is all for today's lecture. Thank you all for your attention and see you next time.